Hi, everybody. I'd love to introduce Chunmiao Zheng from EIT and SUSTech, and he's an expert in modeling the subsurface water systems. Welcome.
Thank you. Should I go ahead?
Yeah, go ahead. Yeah, I want to maximize your time.
Okay. Thank you very much, Greg, for the introduction. And I'm very pleased to have the opportunity to share some of my work here today. Let me check the time here. Okay. Here is an outline of my presentation today. First, I want to give everybody some background on groundwater and groundwater modeling, so we are on the same page. And this, I show you the cover image of the United Nations World Water Development Report for 2022. And the title is Groundwater, Making the Invisible Visible. So groundwater is still invisible to many people. So why is really groundwater? For audience not familiar with groundwater, it's referred to water beneath the Earth's surface. So beneath the surface, all water near the surface, the pore space is only partially filled with water. So we refer to that as an unsaturated zone. And then when the pore space is filled with water, groundwater, that's the saturated zone. Between the two, there's the water table. Okay? And there are three primary forms of groundwater occurrence. First, the water through the voids in sands and gravels and silt. We refer to that as a porous aquifer. About 60 to 70% of all aquifers in the world. And then the water through the fractures in bedrock, such as granite and basalt. About 20 to 25% of aquifers are fracture aquifer. And water through the channels and caves dissolved from carbonate rocks. We refer to that as a karstified aquifer. About 10 to 15% in the world. Okay. And I want to emphasize using this cartoon, the groundwater and surface water are really a single resource. You can see on the left here, the groundwater coming from infiltration into the underground, and then under natural conditions, discharged to river with surface water. And the water table is quite near the land surface, so vegetation is growing well, so it's a healthy ecosystem. But if you pump groundwater too much, overdraft, and then water table declines, and then actually the reverse flow from the surface water to groundwater. And then the water table may be too deep to land surface, some vegetation will die. So this is stressed condition. So to protect the ecosystem, and you really need to consider both groundwater, surface water together and manage them conjunctively. And groundwater is very important to humanity. I want to just show you the talk from John Cherry, who used to be at the University of Waterloo in Canada, a leading figure in our field. And I invited him to give a lecture in my university in Ningbo, end of last year. And he talked about how groundwater is important in terms of water, food, poverty. And he mentioned that groundwater is at the heart of a global water crisis, and with some statistics, such as 99% of all liquid fresh water is groundwater, and about half of humanity drinks groundwater. And some countries, the percentage is much higher. For example, in Denmark, over 90% people drink groundwater. And then 70% of global food production from irrigation has groundwater origins. And much of this water is from irreversible a depletion, overdraft of groundwater. And then nearly all aquifers in use today are contaminated to some degree, but the health impact are minimally quantified. So a lot to do in this field. And I recently did a little analysis looking at using a Scopus database. And for the past 10 years, about 300 publications within the category of water science and technology. And looking at the top 50 key phrases, you know what, groundwater ranked first. So for researchers, I think the groundwater it has been recognized to be a very important topic, but it's not yet because it's hidden, it's invisible for public. I think it may not realize how important groundwater are. So, but at least for the research community, I think groundwater and in the water science, groundwater is very important topic. And also, I want to mention this article that I wrote with Steve Goridic at Stanford. And the title is Global Challenge and the Groundwater Management, a Global Change and Groundwater Management Challenge. And we identified 6 areas or 6 dimensions of groundwater vulnerability. In other words, we found that groundwater that play a central role in at least 6 areas that we are familiar with, and they are very important to our life, such as geological hazards and human health from groundwater pollution. And I mentioned earlier already the irrigation of a lot of food production depend on groundwater, and the energy like fracking and also biofuel depend on water, groundwater, and then the ecosystem health and the conflict between countries, between states in transboundary aquifers. So you can see the groundwater is really the fundamental to many things we deal with. Okay, since this talk is it's a modeling, a Google modeling talk, so I have to show you some equations. Okay, so for groundwater dynamic, the first equation is the basic governing equation. So it's for water level and hydraulic head, the space 3D, and also the time variant, so transient. So basically is a second order partial differential equation. And the key parameters are hydraulic conductivity, which is the ability of rock formation to transmit water, and also the storage coefficient, specific storage. So that's the first equation. And the second equation describes the mass transport in groundwater. So the variable is the concentration, solute concentration. And here it's a mixed order, first order advection, and the second order dispersion equation. And again, it also include reaction. So in my talk and later follow up, I will use case studies which solve both equations. And the standard numerical solution techniques are usual suspects, such as finite difference, finite element, and finite volume. There are other variations of the governing equation to deal with special cases with different type of media, subsurface media, but then those 2 are the most basic equations for groundwater flow and contaminant transport. And in my today presentation, I will not go into any details about the solution techniques, but for those of you who are interested in this topic, you can refer to references. One is applied groundwater modeling that describe most of modeling for flow modeling techniques. And lead author is Mary Anderson, my PhD advisor at the University of Wisconsin-Madison. And also my own book with Golden Bennett, Applied Contaminant Transport Modeling. And this one I deal with mass transport in groundwater. Okay, the second topic I would talk about is the changing nature of groundwater in global water cycle. And this is the title for a review, a paper my research team published early this year in Science. And this is one of the very few papers that describe groundwater actually in Science. And with this work, we synthesize all the recent study on groundwater and compile all the data and updated the global water cycle with the different components, including storage and fluxes between different components. So this is quite a significant result based on all a review of all the recent work in the area. And the overarching conclusion is the role of groundwater in the global water cycle is becoming increasingly dynamic and complex. And the security of groundwater resources face considerable threat worldwide. And we describe those, what are those threats are in the review paper. Okay, and if you're interested in this topic, obviously you can look at the paper, but I won't go into the details. What I listed the 10 key points from the review paper, I just to share with you. And first is that the climate change and anthropogenic activities have significantly impacted groundwater system worldwide, changing everything. And the groundwater depletion has occurred globally, including like Central Valley, California, and High Plain, California, and North China Plain. It has intensified over recent decades. So this is really a global concern. And then we describe some comprehensive management strategies which might be needed, might be used to mitigate the overdraft groundwater issues. And then we also identify some major research gaps in groundwater research, and also pointing out how important, very important to have observational data set, doing more monitoring network, and also talk about the important to deal with both physical and virtual water cycles that are embedded in the global food trade. Okay, so we also need to deal with like ecosystem health and using interdisciplinary approaches. So very quickly, those are some of very key points from this review paper for those interested in this article. Okay, the major part of my presentation will be on 2 case studies in modeling groundwater dynamics. The first case study here is modeling groundwater dynamic in the Asian water tower. And this is in the Tibetan Plateau. I think many of you heard of this Asia's water tower, but it also has been referred to as the 3rd pole of the world because it's the highest on the land on Earth. And it's a total area of 2.5 million kilometers square. And it provides water for about 2 billion people downstream. So it's very, very important region. And my team, a research group, has been studying the water issues in the water tower for the last 8 years. And we focus on this Yaluzhambu River Basin, which is about 240,000 kilometers square. And I'll just show you some image of this river basin, Yaluzhambu River, from upstream, middle stream, and downstream. Very scenic. And to model groundwater dynamic in this type of region, in Tibetan Plateau, really very challenging, extremely challenging. I just listed a few here. First is this mountain hydrology, complex terrain. So there's introduce a lot of complexity. And then this cold region, permafrost, induce a lot of uncertainties in hydrological processes. And importantly, in this type of region, very limited data available. So that's a major concern. So this region has been referred to as the last frontier of hydrological research, hydrological sciences. Okay, but we still need to study this type of region. It's a very important, as I mentioned, and for the water supply, for the global this water supply. And the key questions in our research for groundwater modeling, we want to quantify composition of the river water. Where does the river come from? That's the first question. So for this region, we developed comprehensive hydrological models for this. It's quite a complicated effort. And so we have a model including both account for groundwater and the rainfall, surface water, and the glacial snow melt, and evapotranspiration, and so on. And here are a couple of references published in the WR and the geophysical research letters. And then we built the model and calibrate the model, and then conduct detailed analysis. And then we were able to quantify the runoff in Yaluzambu River, 40% coming from rainfall, 40%. And then the glacial snow melt, about 24%. And the groundwater direct discharge to the river, the base flow, 36% overall. And then there are more groundwater discharge into river in the upstream, and less in downstream, but overall it's about 36. So those numbers are quite important in terms of management for water resources, and for the conjunctive groundwater surface water management. Okay.
So
Yeah.
How much do you need to know about the underground seismology in order to do these models? Because this is a very large area with very different, seismologies, and like the underground porosity and that kind of stuff.
Yeah, that's what, as I mentioned, that's the really challenging, the limitation of this type of study. So we do have some information, geological information. So we built our all available information, and some also a borehole. So we built the geological model, and then including, you mentioned, a fault tectonic and porosity and so on. Okay. And then in this type of our work, we usually, for a closed basin, so right, you can do a water balance, like a rainfall and glacial snow melt and permafrost thawing, and be the input and the inflow, and then ET, evapotranspiration, and stream flow, outflow. And then input minus output should be equal to the water storage change. But in our case, we find that they are not balanced, they are imbalanced. So we hypothesize, and we are pretty confident this is right. There's significant amount of water actually discharged out of this basin through the deep fracture bedrock aquifers, because in this basin a lot of faults, big faults, and very deep, and they might carry some groundwater out of this basin. So this basin is not the closed basin. You cannot do a simple water balance. You need to look at the large area, large region. So we published this work also in WR, so regional imbalance. And another thing you just may ask about this is complexity, geology, and also the data, lack of data. So we also conducted a study and using great satellite data. This gravity data, this is a very important approach. So in this case, we can look at the very large region and then look at the storage change based on the gravity anomaly. So in this work, we found that actually groundwater storage, the liquid groundwater storage in the Tibetan Plateau is increasing, but they're increasing because snow and glacial melting. Okay, so this work was published in the Geophysical Research Letter, and then that was picked up by the Nature as a research highlight with an interesting title saying that Asian water tower is brimming with water, with glacial meltwater. But they are coming from the slow melt. So this is tricky. How long this can last? Because eventually this permafrost and slow and glacial might disappear as climate warming continues. Okay, so this GRACE, the geophysical, this remote sensing work, very important, provided this basin-wide storage change. So we were able to compare our model simulation with the satellite data information, and then they agree quite well. And so this gives us the confidence that the model will be reliable. And then based on our calibrate the model, we were able to do a lot of analysis. And as I mentioned earlier, that a lot of water might go from surface to groundwater and to out of this basin, and even to discharge directly to Indian Oceans. So this is a very large scale groundwater dynamic movement. And then another question that we ask, will the water tower eventually run out of water as the snow melt, the glacier disappear? And then the answer is no, the water tower will not run out of water because there will be a precipitation. But we might lose the buffer effect of glacier and snow covers and be more dependent on precipitation. So this diagram shows you the contribution of a glacier and snow melt will eventually decrease based on the different climate scenario, from 2000 to 2100. So keep decreasing. Permafrost. Yeah.
But if the buffer is lower, does that mean the variability in water, like availability, will be higher?
Yeah, buffer mean that can store a lot of glacier, a lot of snow that keeping a lot of water there. If they all disappear, then we really only depend on precipitation.
Okay.
So that's that we talk about this buffer effect. And the permafrost is another thing. Permafrost contains a lot of solid water in underground, and then they are thawing very quickly. So how this permafrost degradation and thawing impact stream flow, impact ecosystem. So that's another thing we've been studying. And then permafrost degradation modify, change hydrology and landscape. And we, in our study here, is for a couple of papers in environmental research letters, and we quantify the spatial temporal dynamic of permafrost active layer thickness. So-called ALT basically is a maximum thawing depth from land surface down. So this is we quantify, and then we also project into the future. So based on different scenario, and from 1980 to 2100, essentially by that time, much permafrost would have disappeared. Okay, so that's a major impact. So we look at what happened with this permafrost degradation. Essentially, the thawing, the active layer thickness were like 4 centimeters per year will increase, and that will lead to a direct surface runoff decrease, actually, like 0.65% cubic kilometer square per year. But the stream flow will increase because stream flow, the permafrost thawing will directly lead to a discharge, a base flow to stream. So those numbers are quite important threshold values for the groundwater dynamic in this region. They have a major implication for water management in the future. Okay, so that can kind of summarize our study on the groundwater dynamic in this Tibetan Plateau on last frontier of groundwater research. And then the next case study, a little different. It's integrated modeling of flow, soil erosion, and nutrient dynamic. This time, now we account for both the flow and the mass transport in coastal aquifers. And the background is that in globally near the coastal area, near the near shore coastal areas, significant eutrophication and also hypothic areas due to excessive nutrient from the land, just due to human activity and pollution. So they have a major like algae bloom affecting water quality and the water environment ecosystem near shore. So this is show you the global distribution. So our group has been doing this study for a few years and looking at the Greater Bay Area of China, Guangdong province, and Hong Kong, Macau, major economic region of China, Greater Bay Area. And then interestingly, we just got this paper as an author proof yesterday. So from WRR. So this study I thought is very interesting because this study is a very large scale and involved application of AI and they use the big data and involve multidisciplinary research. All the attributes I think represent the future of groundwater modeling. Okay, so I will discuss a little bit of this study. So this is an area of 450,000 kilometers square, so very large region. As I mentioned, a lot of intensive agriculture and human activities in major cities like Guangzhou or Shenzhen and Hong Kong. And for our approach, again, is based on the modeling, and this time it's not just the groundwater modeling, but also surface water and the land surface eco-hydrological process. And so we developed a couple of simulation model called HayFlow, hydrological, ecological integrated watershed scale flow model, and based on the USGS GS flow. And here you see the discretization of both surface water and the groundwater domains. And then for this particular work we developed like soil erosion and the nutrient nutrient transport module. So we can examine both flow and nutrient dynamics. Because our study area is a coastal area, so one more complexity is the ocean dynamic. Because the ocean dynamic and tidal effect impact this is how much nutrient can discharge into the ocean, right? So this is the boundary conditions important. So in our work now, we actually used a popular marine model, FVCOM, to simulate and predict the ocean dynamic, and use that as a boundary condition for our hydrological model. Okay, so this is a land-sea couple model. And then for the groundwater, it's very important because we simulate the surface water groundwater interreactions, and also groundwater might discharge to ocean directly in this submarine groundwater discharge process. And for groundwater, this is the subsurface parameterization. Different color show the different hydraulic conductivity. That's the main controlling parameter for groundwater flow. Okay, and how we got the data? We have a lot of boreholes, and then we have a geological map, and we analyze the information, and then come out with this parameterization scheme. So different layers and different zones. Okay, now I mentioned already earlier in this study, we actually use quite a bit of big data and machine learning to help us, because this very large region, a lot of contaminant sources, including point source and non-point sources. One major point source is this the wastewater treatment plant. There are dozens of them. And each treatment plant will treat the contaminated water and effluent, discharge them into a river, in the lake, surface water. And even though they have been treated, but still they contain a lot of nutrient, a lot of low-level concentration, which still pose a threat for the area. So it's hard to estimate the discharge for each wastewater treatment. So we use this big data, which is based on population migration data from Gauder map, which is similar to like Google map, and then also based on meteorological data. So we were able to use the big data and then using a machine learning approach. And we do a very good job actually predicting the discharge for all the wastewater treatment plant for the Greater Bay Area. And here on the left, you see the different intensity of discharge. And not only the amount, total amount, we can even identify the contribution, quantify the contribution of this the effluent. Some of them from precipitation, mixed with precipitation, and also infiltrate groundwater into the pipe effluent. So we have not just the total amount, but also the contribution from different source. Okay.
So, question.
Yes.
This is a rather challenging modeling problem. So it looks like you don't know where the sources are, and you have just the population and the downstream measurements. Is that right?
Yes, we have some we know, like agriculture sources. We estimate that fertilizer application, but this particular is a wastewater treatment plant. There are many of them, and it's very hard to get the data. So we get the few data, and then we use this machine learning and the big data, like population migration, and then we estimate for all of them. And then we checked several treatment. They match up very well. So this is one way to deal with it.
And do you have like nitrogen and like a chemical sensor data from downstream? Is that how you
Yes. We have quite a few of chemical sensor data at the cross section at the rivers. Yes. And then we use that for our model calibration. But here we particularly that from the wastewater treatment plant, those plants won't give us any data. So it's very hard. So this we do. So we try our best to gather data from different sources. And
so this is like very interesting.
Yeah.
This has many analogs. I'm thinking air monitoring, where you say sources of methane from satellites, sources of carbon dioxide. I guess, can you give some general idea of how much sensor coverage you need to start attributing the causes of, like, it's this farm or this region's farm, that the region farms that are causing, let's say, I'm thinking Gulf of Mexico. A lot of nitrogen goes down to the Gulf of Mexico via the Mississippi and so on. To what extent is it possible to attribute the outcomes to the sources?
So your question is how much data distribution data we need to actually to validate the model.
Well, and actually confidently attribute. It's like, it's this, let's say, 20 kilometers by 20 kilometers. There's farms in this region that are causing this algal bloom, or this other region, or maybe it's 100 kilometers by 100 kilometers, or something even larger. And how much data do we need for any kind of attribution?
Yeah, I think maybe this will answer your question. So it's really hard. I mean, for hydrological model, we place the sensor at some groundwater wells and some rivers. But for like a coastal area, it's very difficult, and then such a large area. So we actually, my team, we developed this remote sensing approach, and then we actually can directly observe, detect the algae bloom for coastal region, and not just in our study area, but also globally. And this work very exciting. Actually, was published 23 as a Nature cover paper. So that we use this approach and then get a lot of data. Now we can compare this remote sensing provide a very cost-effective, very quick, efficient way to get a lot of data like algae bloom, water quality, and then we actually compare this then with our hydrological model, because hydrological model is process-based. We simulate directly how much nutrient from our study area discharge into the ocean, and then we compare. And first, this is a B here, the top right, and then is our remote sensing data, and then the lower left is the simulation from the physical-based model. First, you look at that, they don't agree too well, but we realized that actually remote sensing has limitation as well, because over cloudy days, they don't have data. It's just the remote sensing. In this case, they only want it weather is good without cloud. So when we remove the simulation result, where without the remote sensing data, only compare simulation with remote sensing data on those states with the data, so they actually agree much better. So this actually is one of the, I think the very first one, we actually directly compare our physically based model result with the remote sensing data. And remote sensing cannot do prediction because they just give you the observation. But the physically based model then can predict way into the future. So this is a combination of the two. I think is a very powerful tool.
So another question on this one.
Yes.
Are clouds correlated with the phenomenon in question? So do you have more algal blooms when you during the season when you have more cloudy days, or the other way around?
Yeah, good question. So you are saying that cloudy days different. There's no particular pattern in this case. We just our team just utilize whatever available, download all of the remote sensing data available. So in this region, and it's also depending on the different region. For the Greater Bay Area of Guangdong, Hong Kong, Macau, a lot of cloudy days. Actually, 2/3 of a year is cloudy days.
Well, what I have in mind is something like Indian monsoon. During that whole season, you're going to have many more cloudy days than during the other times. And presumably, the hydrology, the biology of the the algae will be different during the season. So, if your data collection is omitted in a biased way, your validation is going to be biased in this particular weird way. So, is that true? And if so, how do you undo that bias?
So this is a limitation of this remote sensing approach. For now, it's constrained by the weather. But our physically based model can actually can simulate continuously.
So is there a way? So that actually makes sense. So your simulation doesn't care about this, but
That's
your
right.
validation, do you need to count the cloudy days as being, well, like undo the bias? Let's say you count the lower population days, the cloudier days, count the air there higher because you don't get as many of them in your training set. Or you just say on non-cloudy days, this is our air. On cloudy days, we don't know.
Right. I mean that's what the approach. So for the comparison here, I say okay. For the cloudy days, I don't compare them directly. So because I don't have data here, so
Got
I
it. So
only
this
have
is satisfied comparison. Okay.
Okay. I think I have kind of very quickly giving you the two quite different case studies, and the reason why is that this very cold and high altitude region, and but mostly on water dynamic, groundwater dynamic, and the other one is where groundwater is part of disciplinary. Which is study looking at the very complex flow and soil erosion, because soil erosion carry a lot of nutrient and then ocean dynamic. So I think kind of giving you a taste of the complexity of groundwater process. Now I want to offer a little bit of future perspective. I have to mention that I just a couple months ago attended this conference at Princeton. It's called Mud Flow and More. This conference actually is an international groundwater modeling conference since 1998, originally held for many years at the Colorado School of Mine, and recently just moved to Princeton. And this year, the theme for particularly this year is AI, global change, and the future of groundwater modeling. So this is a very relevant theme for what I'm talking about today. So one particular trend for the future we identify is this groundwater modeling for a very large scale global energy and water exchange context. So this is GWAC is a UNESCO program for really looking at the global climate, global circulation, and Earth system community. So we have we form a working group. I'm one of the members. So try to try to advance groundwater modeling and in this GWAC framework. And we did a presentation at the modeling conference. We know the Earth system models are widely used now, and it's a very powerful tool to study the climate system and the interaction with surficial process. But all the Earth system models really don't consider groundwater yet, or treat it extremely simplistic way. So groundwater is the missing link in Earth system models, and we are trying to do something to mitigate the issue, to improve the representation of groundwater processes in Earth system models. Now, it's very challenging in representing groundwater in Earth system models because the scale, okay, and the challenge is like the data availability and quality. We are talking about in a small region, basin is difficult. Now we are talking about global and continental, it's very difficult. And the model complexity and the scale, how to balance the complexity and computational burden, and also the climate and human impact on groundwater process. You need to be represented in this Earth system model. It's difficult to do. So as a groundwater people, we really need to find a way to develop method and techniques and the parameterization techniques for large scale groundwater modeling, ranging from global, ranging from continental to global. And there are only a handful of very large scale studies. Here are just a few of examples of global scale groundwater model. I list actually most of them probably. The groundwater global scale groundwater model is really just at the beginning of our research. And then here's another example, fairly advanced example of a Canada One water, which is from University of Waterloo and Ed Dickey's group. And this is including all of Canada and also some part of transboundary United States. So it's if a watershed go over the border, so it will be included in this model. Here you show the model domain and the different type of data required for this type of modeling, including bedrock and soil type and surface water network and rainfall, ET, and so on. So this is an example. And then I also would like to show you a couple more recent, is like a national scale with fairly high resolution scale model. One is in the United States, and the other one from Rui Maxwell's group at Princeton. And my own group has also developed a national scale for entire China, mainland China groundwater model. So I just show you this is an example, a little bit couple thought on this model. What can we do with this model? For it simulate the water table depth, is dynamic depth. All the way from 1945 to now. And then incorporating future climate scenario, we can project into the future. So that's quite useful for long-term water management planning. This is the water depth for China 2020. So you can see from less than 1, very close, like a wetland, near land surface water table, and all the way to a greater than 100 meters. So very deep aquifer. And then the model started from 1945. At that time, there was no pumping, assume. So it's a like 30 initial condition. And all the way to now, you can see the cumulative groundwater pumping, the storage depletion. So again, from less than 1 depletion all the way to greater than 50 meters. So groundwater table really declining because over pumping for agriculture, for drinking, for industrial use. Okay, so this is and then this kind of information we have observation network to verify, to check. So we have lots of wells to water measurement to compare the simulation result. And then we can also look at the groundwater storage trend, long-term trend, and the water depletion. This is how much groundwater storage is being depleted. You can see the blue line from our study for all the way from 1945 to 2020. You can see quite interesting. After some increase in the 80s, 90s, and now kind of depletion has plateaued, stabilized. This is because some measures by Chinese government, for example, south water to north water transfer, that really reduce groundwater pumping. So this is important for in terms of long-term national scale planning. And it's interesting, our result, the blue line is quite significantly different from some other studies, like this red line, because it's based on water balance without considering groundwater dynamic. So this is obviously a major implication. It's very significant because the red line still showing increasing depletion. So it's very different, the trend. So I think I have given you a kind of very quick introduction to this groundwater dynamic modeling recent advances. Here is some take-home message. I don't need to read it, but essentially, I like to say it's groundwater. It's really important for both people and ecosystem. And then, as in our review paper showed, groundwater is undergoing a rapid change due to climate change and increasing human disturbance. And within all of this different context, the groundwater modeling is one tool that's really important, crucial to understanding and managing groundwater. And in terms of current trend, the future direction in groundwater modeling, I can summarize them as follow 4 points. One is the scale. It's going larger and large scale. Now we have covered entire basin, like the Greater Bay Area, and also continental scale, like entire U.S., entire mainland China. And even global scale, I'll show you a few studies that looking at the entire global picture of groundwater system. Now we're also going higher resolution because this is what the subsurface groundwater is very heterogeneous media. So we need to, if we want to incorporate this, account for heterogeneity, we need to increase the resolution. And then more comprehensive, we have a multi-process. As I show you my second case study, we look at the soil erosion, look at the nutrient dynamic in the Tibetan plateau work. We look at the permafrost glacial and so on. So multi-component, and also groundwater and vegetation, ecological system, and then some physical, chemical, and biological interreactions. And finally, the innovative approaches we have now need to utilize in the new technologies such as machine learning and AI and big data and cloud platform. For this global continental scales, like tools like such as Google Earth could become very handy, very, very useful. Okay, so that, Greg, that's all my report for today. Thank you very much.
Yeah, well, thank you very much for your time. And let me ask just one more question.
Yeah.
A lot of your work is emphasizing the physics-based simulation approach, and a lot of stuff like in Google incorporates a lot of machine learning, unmeasured, basins kind of things, where we may not have enough information to do physical-based simulation. So, what are your thoughts about kind of hybrid approaches that leverages as much physics as we have and fill in the gaps with data?
I don't quite get your question. So you're saying that the Google team mainly look at the work on the physical aspect, right?
Well, no, it's more like, so for example, I'm thinking surface hydrology right now, where you say, I'm not sure exactly what the roughness of the river is, exactly how much water is going from riverbed into the groundwater. So I'll, get the data I have from the gauged river basins and, project out to ungauged ones, just based on not a detailed physical understanding, but a rough, correlative understanding. And they get good results from that. And my impression is because we just have so little data about the subsurface geology of these basins. That's why physical models have challenges. But then I want to get your thoughts about kind of that connection. Like, when is one better than the other? How can they work together?
So the data it will always be limited. So what we can do is to looking at multiple source of data. So for either surface water or groundwater, we have traditionally we need to make a physical measurement like a water level, like a stream gauging stuff, right? But the trend is that we can utilize other type of source of data, like I mentioned, remote sensing, very very powerful, and then we can use the machine learning tool and the AI to really help us to fill some of the gap in the data, and also to learn to transfer from one type of engaged to gauged to engaged. This is a challenge I think we are finding a way to deal with it.
All right, thank you. Well, this is fantastic. Thank you for your time.
Thank you. Thank you.